Hi, everyone. So, maybe a good evening. And today we are very happy to have Professor Netta Engelhardt from MIT and as our Colloquium speaker. And let me first briefly introduce her. So Netta got her PhD from University of California, Santa Barbara. And then she spent some time at Princeton as a postdoc. And then 2019, she's joined MIT, and she has published many important influential papers, in particular related to some quantum aspects of gravity and holography, and in particular black hole information paradox. And today, actually, she's telling us about the black hole information paradox of resolution on the horizon. So Netta, please start.
Right. Thank you very much for the lovely introduction, and thank you for the invitation to speak. Wish I could be there in person, but this will have to do. So I'm very excited to tell you about some recent developments on the black hole information paradox. And these developments have been so rapid and so monumental that I'm very emboldened to say a resolution on the horizon, or rather to suggest it with the question mark. So I'm going to begin with some background on the black hole information paradox. I'm not going to assume that you necessarily know exactly what it is. So the way this talk is structured will sort of start at a very, very high level and gradually progress to lower and lower levels, and not at the super technical level, but hopefully there's something here both for people who are seeing this for the first time and also for people who are experts at the very end. So the most basic question that we can ask about the black hole information paradox, of course, is what is it? So the black hole information problem at the sort of the highest level, the most general statement that I can make about it is that it's a conflict between the predictions of quantum field theory and the predictions of general relativity, of classical gravity, in a regime where the two theories should be decoupled. So we don't expect, approximately decoupled. So we don't expect that they should be able to give us contradictory predictions about the same phenomenon. And that is a problem that has been around for a long time, going on almost 50 years at this point. And we are, in my opinion, finally getting closer to resolving it. Now, you could ask, okay, well, it's a problem, but why do you bother studying it? And of course, paradoxes are fantastic. Paradoxes tell us that there's something fundamental in the way that we understand the theories that are describing our universe that is wrong, and it's telling us where to look. And in particular, since this paradox involves classical or semi-classical gravity and quantum field theory, it's telling us something about quantum gravity and the relationship of quantum gravity to the semi-classical regime that is the one that we observe around us, which is essentially gravity and quantum field theory in the decoupled limit. So in our quest to understand the universe, we of course need to have some understanding of quantum gravity, and the black hole information paradox is one way of pointing the way towards that understanding. There are several other reasons to study the black hole information problem, but to get into those reasons, I'll have to tell you in a bit more detail what the problem is beyond just a conflict. So we'll get to those reasons shortly. Now that we know what it is on a very high level and we have some motivation for studying it, the next natural question, of course, is how do we make progress on it? And indeed, it's a very stubborn problem, and it has been very difficult to make progress on this for a long time. But as I'm going to show you in this talk, the past 3 years have just seen an acceleration of our progress and understanding on this problem. So this talk is mostly about number 3, which is how to make progress on the black hole information paradox. Now, let's get a little bit more, now that the sort of 60,000 foot level, maybe let's get down to the 30,000 foot level of what the black hole information paradox is. So I've been using this phrase semi-classical gravity a little bit. Let me define what I mean by that. I'm talking about the weakly coupled limit of quantum gravity. Semi-classical gravity is essentially what we observe in experiments around us, as of now with our current technical tools. The gravity and quantum field theory, quantum mechanics are very, very weakly interacting, with the parameter that controls this interaction being g Newton times h bar. So it's a very small parameter. That's the semi-classical gravity limit. And we expect that semi-classical gravity is sort of an effective field theory that should be valid in situations where we're talking about low energies or equivalently low space-time curvature. So as long as the parameter gh bar is small compared to the space-time curvature, compared to the energy of the particle is under consideration, we expect that this weakly coupled limit of quantum gravity is a valid description of the physics that we're observing. And in particular, that regime includes the event horizons of sufficiently large black holes. So sufficiently large black holes, and I'm not talking about black holes the size of M87, much smaller black holes are also fine. Near the event horizon of large black holes, of such black holes, macroscopic black holes, we expect that semi-classical gravity is also valid because these event horizons are very, very weakly curved. So the curvature there is small. The semi-classical gravity limit should be a very good description. So the information paradox, again, at this sort of 30,000 foot level, is the prediction, a prediction of semi-classical gravity that contradicts the sort of basic principle of quantum mechanics of unitarity. And it does that at the event horizon of a black hole. So that is a regime where we expect that semi-classical gravity is valid. And if we want to, we can't have semi-classical gravity, it seems, and unitarity of quantum mechanics at the same time, unless we modify semi-classical gravity at the event horizon of a black hole, which is a regime where we do not expect that semi-classical gravity requires modification. So in a nutshell, this is the problem. We have two conflicting predictions. Both of them are theories that should be valid, and they contradict one another. So a little bit more on this, on how this contradiction comes about. So semi-classical gravity predicts that it's possible for black holes to evaporate. And we'll talk about the process of how that's supposed to work shortly. But for now, just take it on, take my word for it for the moment. This is a prediction that comes from semi-classical gravity. Black holes can evaporate. And the process of black hole evaporation appears to violate unitary evolution of closed quantum systems. Now, this is, of course, something that we expect must be true. Unitarity of quantum mechanics is sort of inviolable principle. And so, and as is Einstein's theory of general relativity also appears to be valid. So again, this is just driving home the point that these are two postulates or principles of the universe that we don't expect to have to, we don't want to give up either one. And at the same time, they don't agree with one another in a regime where they should. So this concludes the 30,000 foot perspective on what the black hole information paradox is, and we'll get to the sort of 10,000 foot view shortly. But let me give a 30,000 foot view on the why. Why do we study it? Before I said, oh, it's going to tell us something about quantum gravity, which is of course a very valid reason. But now that we understand that it has to do with unitarity, we can understand there are other reasons, very important ones to want to study it. If we allow for violations of unitarity of closed quantum systems, which is what semi-classical gravity appears to want, that is, if we allow for information loss, then we have a catastrophic loss of determinism in physics. Essentially, what it means is that if we take the universe today, the state of the universe today, and we try to evolve it backwards, then it's backwards in time using the equations of motion, then it would be simply impossible for us to post-dict the past. And physics is supposed to be both post-dictive and predictive, which means that we have a loss, basically a fundamental loss of determinism in our ability to make post-dictions and by time reversal predictions. Another reason is that black holes actually exist, we suspect. There's excellent evidence in favor of the existence of black holes, both indirect and direct evidence. So there's a definitive answer to what actually happens at the event horizon of a black hole. This is part of the universe, of our universe, and we would like to understand it. Without an answer to the question of what happens at the event horizon of a black hole, our description of physical phenomena in our universe is incomplete. And so there's an urgency to understanding the resolution of the black hole information paradox. And of course, there's the third reason, which is really the first one I mentioned, which is that the black hole information paradox has a lot to teach us about quantum gravity and the way that we can settle quantum mechanics and general relativity with one another. So I mentioned that the past 3 years have seen a dramatic acceleration of progress on the black hole information paradox. So what changed, 3 years ago that caused this dramatic acceleration? And what was the perspective before 2019 versus the perspective now? So pre-2019, the prevailing perspective in the field was that quantum gravity is necessary for information conservation. In other words, if you're working purely within the regime of semi-classical gravity using semi-classical tools, you're never going to see that information is conserved. So the basic idea was that all tools, all calculations that you do in semi-classical gravity are simply inconsistent with the unitary black hole evaporation process, and that semi-classical gravity simply predicts that information is lost. There is no calculation you can do using semi-classical tools that will indicate otherwise. Now, what happened in 2019 was a purely semi-classical analysis using just semi-classical tools that was consistent with unitary evaporation. And that sort of opened the floodgates for us to use tools from semi-classical gravity and understand the ways in which we can see information conservation within semi-classical gravity or within the embedding of semi-classical gravity in quantum gravity. So I think it's safe to say most of us, certainly I thought it was impossible to do this before this calculation in 2019. And when we did this calculation, we were both shocked and extremely excited because it meant that all of a sudden we had this new arsenal of tools to attack this problem. So this is basic introduction, and now we're going to get more into the details of what is the black hole information paradox, how things stood pre-2019, what happened, what was the 2019 calculation that changed it all, and I'll also discuss the current work since 2019 towards a resolution. So all of this will be more technical than this sort of 30,000 foot view introduction. So I'll begin with the black hole information paradox as it was formulated in the 1970s. And our story really begins, as most good stories in physics do, with thermodynamics. So there is a result in classical gravity, which essentially says that black holes in classical gravity have no microstates. And this is sort of called the no-hair theorem. And this theorem prompted a Gedanken experiment by Wheeler that was very puzzling. So Wheeler said, it's called Wheeler's teacup experiment. Wheeler said, okay, black holes in classical gravity, black holes have no microstates, then they have no entropy. Now consider taking a hot mug of tea, which certainly has thermodynamic entropy, and throw it into the black hole. Well, once it's inside the black hole, then the teacup has vanished from the rest of the universe, has become part of the black hole system, and the black hole system has no entropy. So you've just managed to decrease the entropy of the universe. And you can do this an arbitrarily large number of times with arbitrarily large number of entropies, a large amount of entropy, and just keep on decreasing the entropy of the universe in gross violation of the second law of thermodynamics. And one of my favorite quotes of physics is by Sir Arthur Eddington, which says, if your theory is found to be against the second law of thermodynamics, I can give you no hope. There's nothing for it but to collapse in deepest humiliation. So Wheeler, of course, preferred that gravity, which had numerous tests at that point, would not collapse in deepest humiliation. And so he tasked his student, at least the story goes, that he tasked his student Jacob Bekenstein with resolving this problem. And in my opinion, that's a somewhat cruel problem to give as a graduate student, but Jacob Bekenstein rose up to the challenge, and he gave a very novel understanding and proposal for what's going on here. So Bekenstein proposed that black holes actually are thermal objects. They have a temperature and they have an entropy, but not due to classical gravity microstates. There are none, but due to quantum gravity microstates. That black holes have quantum gravity microstates even though they do not have classical gravity microstates. And he further proposed that the entropy of the black hole is computed by the area of its event horizon over 4 in-Planck units. And in one of the great coincidences of black hole thermodynamics, this entropy can stand simultaneously for black hole and Bekenstein-Hawking. So this is you know, we can ask, what was Hawking got to do with this? This was Bekenstein's proposal. Well, in fact, Bekenstein didn't know about this factor of 4 over here, which Hawking computed once he also computed the temperature of a black hole, finding that in the simplest case, it's inversely proportional to the black hole mass. Now, I want to emphasize, this is purely due to quantum corrections. This is a quantum phenomenon. The temperature of a black hole, the area of the entropy of a black hole, these are quantum phenomena. In classical gravity, black holes are perfect absorbers, so they don't have a temperature, and they have no microstates, so they don't have an entropy. All of this beautiful story about black hole thermodynamics is entirely reliant on quantum corrections to gravity. Now, let's see how this leads us to black hole evaporation. Well, if you have an object with a temperature, then it's going to radiate. And if the temperature is larger than the temperature of the surroundings, then as it radiates, its mass is going to decrease, at least for a black hole. Now, the interesting thing about black holes, at least in this simple case that Hawking studied, the temperature of these black holes is inversely proportional to their mass, as I already said. That means that actually, as the black hole radiates, it actually gets hotter. And then it keeps on evaporating until it's gone altogether. It explodes in some kind of a massive, you know, very, very hot process. Okay, let's ask, you know, what does that look like in terms of numbers that we might be familiar with? Well, for Sagittarius A star, the temperature of the black hole is very cold. It's 10 to the minus 14 Kelvin. So this is much colder than the cosmic microwave background, for example. This is not something we're not going to see it evaporate. For solar mass black hole, it's still going to be, you know, pretty cold, 10 to the minus 8 Kelvin or so. A lunar mass black hole would be in equilibrium with the cosmic microwave background. So these are black holes that would be just at equilibrium and not actually evaporating. Smaller than that would get you evaporation. And for those of us who are still thinking about coronavirus, a coronavirus-sized black hole would be pretty comfortable at room temperature. So these are just some numbers to ground us a little bit in the what is this process of black hole evaporation. So let's see pictorially how this works. So in relativity, we draw diagrams with time running in the vertical direction. So we imagine at t equals 0, we have some star. So I've suppressed many directions here. So this is meant to be a sphere, suppressed one of the spatial directions, so just a circle here. And so at t equals 0, we have some sphere, it's a star. And this star is shrinking under the force of its own gravitational field. So the radius of the star decreases as we evolve forwards in time. Eventually, an event horizon forms once the star gets sufficiently dense. And the star keeps on collapsing until we get a singularity, or essentially everything in the black hole is being compressed into a region of zero space-time volume. So this is the process of, this is a sort of visualization of the process of black hole formation as a function of time. Now, what about evaporation? How does evaporation really happen, right? We said, okay, it's hot, it evaporates. What do we really mean by that? One way which is very useful of thinking about this is in terms of pair production. So pair production tells us that Springer pair production tells us that there's constantly pairs of entangled particles that are nucleating in the vacuum. That's essentially one caricature of thinking about it, including around the event horizon of a black hole. And so you have a situation where we have one particle over here and one particle here entangled across the horizon. You know, this one gets out, this one stays inside. When I say gets out, it's always outside, it sort of can move away to infinite distance away. And that's the radiation of the black hole. And this particle sort of carries positive energy away with it. You can think of it that way. And then, you know, this positive energy radiating away from the black hole, so the black hole gets smaller until eventually it explodes. So here is again, it's a picture with time running vertically, where we have some, here I've drawn two particles, one inside the black hole, one outside the black hole. The event hits the singularity and the event horizon of the black hole is shrinking in cross-sectional area until the evaporation. And the prediction of semi-classical gravity that we are worried about is that information appears to be lost during evaporation. Quantum information appears to be lost during the evaporation process. So how does that work? So this is a caricature, but it sort of gets the idea across. This is Hawking radiation, the radiation of a black hole in a nutshell. Let's consider the following situation. We have some pure state that collapses into a black hole. It doesn't have to be a pure state, that just makes it a little bit pedagogically easier to explain. You could take a mixed state and still do it, but for clarity and simplicity, I'm going to take a pure state. To take a pure state, you collapse that pure state into a black hole. Now, before the black hole forms, the von Neumann entropy of everything outside the black hole is just the von Neumann entropy of everything in the universe, right? Because there's no black hole. And since we're assuming that we're starting with a pure state, this is 0. Now, once the black hole has formed at intermediate times, the von Neumann entropy of everything outside of the black hole is no longer the entropy of the entire universe, since now we have a non-trivial region that's excluded by restricting our attention to the black hole exterior. We call this the von Neumann entropy of the radiation. We just basically identify the radiation as everything outside of the black hole. Now, the radiation, as we already discussed, is entangled with the black hole. And so the von Neumann entropy of the black hole exterior will be greater than 0, right? This is the fact that we're talking about a subsystem of a larger system in a pure state. Unless we prepare the subsystem in some very special way, the subsystem will be entangled with the rest of the system. Now, once the black hole evaporates completely and is totally gone, then the entropy of everything outside of the universe is once again the entropy of the black hole exterior, or the entropy of the radiation. Now there's no black hole, so everything outside of the black hole is literally everything there is. And now so we expect that this should be 0 once again, right? If the entire universe started out in a pure state and the evolution of quantum mechanics is unitary, then the entire universe ends up at all times in a pure state. It's always in a pure state. So we started out looking at the whole universe, then we restricted our attention to a subset of the universe, then we're back to looking at the whole universe. So we expect that there's a non-monotonic curve for the von Neumann entropy of the Hawking radiation. In particular, we expect that at first, the entropy increases for a while, and since it eventually has to go back down to 0, at some point it has to turn over and start decreasing again. So this is just a statement about the behavior of, if you take a subsystem of a larger system and you gradually make the subsystem bigger until eventually it's the entire system. You get this so-called the page curve. This is what this is. This is what this curve is called. Okay, so where's the paradox? So far, everything seems fine and consistent, right? Well, to compute the von Neumann entropy of the radiation, we're going to need a description of the physics of the black hole event horizon, right? That's everything outside of the black hole up to the event horizon. And again, this semi-classical gravity, this limit where quantum gravity effects are suppressed, should be valid at the event horizon. So we should be able to use semi-classical gravity to compute the von Neumann entropy of the radiation. And yet, if you use semi-classical gravity to compute the von Neumann entropy of the radiation, to compute minus trace rho radiation, log rho radiation, what you find, what Hawking found in 1975, is that this does not follow the page curve. This is the computing the microscopic entropy, there's no coarse graining here, the microscopic entropy of the radiation. And what you find is that this entropy increases, it never turns over, and you end up starting out with a pure state, and you end up with a mixed state. And I want to emphasize again that there's no coarse graining happening here. This is computing literally the fine-grained entropy at every step of the game. So this is clearly a problem, since the fine-grained entropy not being 0 here at the end means that this is not a pure state, which means that we have a non-unitary evolution of our entire universe. Now, how can we see that this curve does that? How can we sort of, without going through Hawking's beautiful but very detailed and technical analysis, can we get an intuition for why this appears to be increasing? And sure, there is a sort of a quick tool for seeing this. So here I've omitted normalization just for simplicity. So we take some state, which is essentially an entangled Bell pair. And we have some we can think one of these particles is Alice falling into the black hole, another particle Bob over here. Now, they start out in this entangled state as a bell pair. But once we look after evaporation, sometime late over here, this very, very late, after the black hole's finished evaporating, well, Alice is gone from the system altogether. And the state of Bob, after the black hole is finished evaporating, is the state of Bob, which always was the state of Bob, which is just the maximally mixed state. So Bob is maximally mixed, and he's literally all there is left. Alice is simply gone since the black hole has disappeared. And so we appear to have gone from the pure state of Alice and Bob to the mixed state of just Bob without any coarse graining. So, and that means that we have grossly violated unitarity. So the initial entropy of the pair is pure. And after the black hole is finished evaporating, the pair is no longer Alice and Bob. The pair is just Bob. And that entropy is log 2, which is non-zero. So the entropy is increased. We went from a pure state to a mixed state, and the system, the Alice and Bob system, was not evolving unitarily. So Hawking's calculation essentially says, all right, we start out with some with 0 here, then the entropy increases as we get these entanglement between these pairs. But as the black hole keeps on evaporating, we just get more and more entanglement between them until the black hole is gone altogether, and this entropy plateaus over here. Now, before I go to the 2019 results, let me actually make a comment. You might say, okay, but surely maybe something dramatic happened over here that restored all of the information. After all, this is no longer the regime of semi-classical gravity. I said when the black hole is large enough, the event horizon is described by semi-classical gravity. But clearly, once the black hole shrinks to 0 size, it's no longer described at some point by semi-classical gravity. And so you might say, okay, so sure, there's a problem, but it's not, semi-classical gravity can be valid and quantum mechanics can be valid, but there's a moment of something very dramatic that happens in quantum gravity here, which is allowed to make large corrections to the very end that restores all the information all of a sudden. And there are many reasons to argue that that can't be true, but the simplest one is to just look at this curve over here. The difference between the unitary curve and the non-unitary curve occurs long before that point where quantum gravity becomes important. We have large differences between the unitary prediction and semi-classical gravity in a regime where semi-classical gravity is still valid. So that is the problem. Fixing things up here to all of a sudden dramatically bring this curve down is not going to solve this problem that we already have over here. And so we really have a problem with semi-classical gravity when it should be valid and it apparently isn't. So this seems like a pretty intractable problem. So you could say, okay, so you've told us the problem, now tell us the solution. All right, so it is hard to see where Hawking's analysis goes wrong. I mean, it's a very, very thorough, very robust analysis. So what do? Are there large corrections from quantum gravity in a regime where there really shouldn't be? Well, 3 years ago, we executed a semi-classical calculation of the unitary page curve, but we didn't use minus choice rho radiation, log rho radiation as computed by Hawking, or would have computed by Hawking if he had done the analysis. Instead, we used a different formula for the von Neumann entropy, which is the formula that comes from holography. Now, the formula is a bit of a black box, but the nice thing about it is you can interpret it as indirect input from quantum gravity. So there's a sense in which quantum gravity is fixing the problem, but it's doing it in a way that doesn't totally remove the validity of semi-classical gravity. It's indirect. Let's see how that works. Well, holography is a duality between quantum gravity, essentially in a box or with anti-de Sitter boundary conditions, to a lower dimensional non-gravitational quantum field theory, which lives on a copy of the asymptotic boundary. So you can think of it as an infinite cylinder. Now, colloquially, we'll often say things like the gravitational theory is the bulk and the non-gravitational theory is the boundary. So again, quantum gravity in ADS, and that's dual to some non-gravitational quantum field theory. Now, one of the most powerful implications of this duality is that a black hole is just an ordinary non-gravitational quantum system. And ordinary non-gravitational quantum systems, ordinary closed quantum systems, evolve unitarily. And so ADS-CFT immediately tells us that black hole evaporation, black hole formation, black hole evaporation is a unitary process. So you could say, okay, that's great. Are we done? We've solved the black hole information paradox. Is it time to find something else to work on? And the answer is no, because we still don't understand how this could possibly happen. We understand now that the answer is that quantum mechanics, the unitarity of quantum mechanics is sacrosanct and continues, and gravity doesn't spoil that. But we don't understand how that works. We don't understand why quantum gravity manages to do this and how. And whether semi-classical gravity does or does not break down at the event horizon of a black hole. So there's a lot that we don't understand. And a full resolution of the information paradox would require that understanding. So what we did in 2019 was not resolve the black hole information paradox, but compute the page curve. So what's the logic, but what was our reasoning? Well, we know that the von Neumann entropy of the radiation computed in this non-gravitational boundary quantum field theory, it must follow the page curve because that's just an ordinary quantum system. And quantum systems are always going to follow the page curve because they are of unitary evolution. Now, ADS-CFT is a dictionary. It relates quantities in the boundary theory to quantities in the gravitational bulk theory. And so instead of computing the von Neumann entropy of the radiation in the bulk theory using Hawking's calculation, we could ask, well, what quantity in the ADS theory is computing the von Neumann entropy of the radiation as the boundary theory would predict? In other words, what is the map between von Neumann entropies in the boundary theory and the gravitational quantities in the evaporating black hole? And I'm just going to mention a brief technical aside here for experts in the audience, which is that technically ADS black holes don't actually evaporate because they're reflecting boundary conditions at infinity. So the radiation just bounces back into the black hole. So in order to force them to evaporate, and this also has the benefit of making them look much more closer to their flat space cousins, we introduce a non-gravitational cold bath at infinity. So in this two-dimensional picture, we have the bulk theory, we have the bath theory. Here, the radiation is bouncing off of the boundary. And at some point, we couple these two, so now there's free exchange. And since the black hole has a non-zero temperature, the bath is a CFT at zero temperature, then the black hole will be evaporating into the bath. In the dual CFT, you can view this as coupling an auxiliary CFT to our dual CFT. And again, this joint CFT plus bath system is going to evolve unitary. So this picture can be understood either in the bulk or in the boundary picture. Okay, so how do we compute von Neumann entropy in the ADS-CFT dictionary? We want to compute the von Neumann entropy as computed by the unitary theory in terms of quantities in semi-classical gravity. That would give us a dictionary between semi-classical gravity and it would give us a way of computing quantities in semi-classical gravity, von Neumann entropies in semi-classical gravity that should be consistent with unitarity. So the von Neumann entropy of the Hawking radiation, and this is a generalization of several proposals of von Neumann entropy in ADS-CFT, but the von Neumann entropy is given by this formula here. So this is in the unitary boundary theory, and this is in the gravitational theory. So here it's given by the area of a surface chi, which I'll discuss more in a moment, over 4 in Planck units, plus the von Neumann entropy of quantum fields outside of this surface chi. So here we have a surface chi, and it divides our spacetime at a given moment in time in two, interior and exterior. And so the von Neumann entropy of the radiation is computed by the area of chi over 4 plus the von Neumann entropy of quantum fields on outside of the surface, on the outside part of the partition. Now you could say, okay, well, what is this surface chi? Clearly, it's not any surface. And so chi is something that we called, that Aaron Wallach called a quantum extremal surface. which essentially is a statement that it's an extremum, it's a critical point of this functional. If you slightly perturb the surface chi, then this quantity, which we call the generalized entropy of the surface chi, is not going to change to leading order in the perturbation to chi. So this is a critical point. This is the way of translating von Neumann entropies in this unitary theory to gravitational semi-classical gravity quantities. Again, this area term is sort of this leading order piece, 1/g Newton, 1/g h bar. So this is a semi-classical quantity that we can compute. So let's do it. Let's see what happens. Well, if we're looking at a sort of a single-sided black hole formed from collapse, initially we compute the von Neumann entropy of the radiation using this quantum extremal surface formula. Well, before the black hole forms, it's just going to be the von Neumann entropy of everything. The quantum extremal surface at early times is just the empty set. Okay. Now, with time, though, we know, and we've seen the Hawking curve, we've seen the Page curve. We know that with time, minus trace of rho log rho, rho rad log rho rad is going to increase. And what happens is that about halfway through the evaporation process, a new quantum extremal surface appears, which is not the empty set. This quantum extremal surface sits just behind the event horizon of the black hole. And as it so happens, its generalized entropy, the sum of its area plus the von Neumann entropy of everything outside of it, is smaller than the von Neumann entropy of the radiation as computed by the Hawking calculation. And so what we find is by using this quantum extremal surface instead of just a standard Hawking calculation, we actually get a decrease in the entropy of the Hawking radiation. And so this calculation, using quantum extremal surfaces, miraculously, in my opinion, does actually yield a unitary Page curve, a curve that increases until the switch over to this new surface. And then as this surface dominates the calculation, the curve starts to decrease. So we've computed the unitary Page curve using tools of semi-classical gravity, quantum extremal surfaces. These are surfaces. Then we've computed entropies of effective field theory. There is nothing here that invoked quantum gravity except insofar as the knowledge that quantum extremal surfaces compute entropies. That is the only place where we needed quantum gravity to come in. And so, of course, the next question is, what does this actually tell us about the black hole information problem, the black hole interior, and in particular, now that we understand and we see in a more gravitational, more geometric way how information escapes, how do we see that the black hole interior is encoded in the radiation? In other words, if information is to be conserved, then after the Page time, as the entropy decreases, information about things that fell into the black hole must start to escape in the radiation. How do we see this in this geometric language? How do we understand this in this, using these new tools that we have for the black hole information problem? And to address that, we're going to take a short detour by asking a different question. What is the significance of this region out of chi? Notice here, it's actually quite important that out of chi is not exactly the event horizon, but includes a bit of the black hole interior. What's the significance of this region? It's clearly important. We're computing an entropy there. What does it mean? So another way of asking this is essentially the reconstruction question in ADS-CFT. We now understand pretty well that ADS-CFT is a quantum error correcting code. And so we can ask, how much of the bulk can we reconstruct from the state of the non-gravitational dual? That's essentially this is effectively the same question. And the reason it's the same question is that everything that lives in out of chi can be reconstructed from the dual theory, from the dual boundary theory. So in particular, what that tells us is that since we have two CFTs, we have the back and we have the boundary CFT. So for those who are familiar with conformal diagrams, this is the conformal diagram here. We have our lower dimensional CFT, and here we have the back CFT, the radiation. Now, this is a moment of time slice. If you're not familiar with conformal diagrams, just worry about this picture. Everything that's outside of chi, between chi and the asymptotic boundary, is dual to this CFT here, which is not the radiation. And because we have a pure state, that in particular means that everything else, everything that sits inside of chi, everything in this wedge here, is included in the dual CFT, in the radiation. And so this tells us, this gives us a geometric picture, a geometric understanding that everything inside the surface, the black hole interior, ends up encoded in the radiation via this ABS-CFT dictionary. So this gives us, again, a better and more geometric understanding of how the information is encoded, how the information about the black hole interior is encoded in the dual theory, in the radiation, essentially. But of course, this still falls short of a resolution to the black hole information paradox. So that leads me to my third and final part of the talk, which is the work towards a resolution of the black hole information problem. So let me recap again what the problem is. The problem essentially reduces to the following. The semi-classical approximation is clearly wrong. It's inconsistent with unitarity. We get the Hawking entropy curve, the one that just increases if you use the naive semi-classical gravity calculation. At the same time, it's not that wrong, because if we use semi-classical gravity, we use this effective field theory to compute quantum extremal surfaces, then we can get the unitary page curve without looking at non-perturbably suppressed quantum gravity corrections. So how seriously are we supposed to take semi-classical gravity? There's one calculation in semi-classical gravity that gives us the right answer, and another calculation that gives us the wrong answer, but it's not obvious how those two are related to one another, and why is it that what Hawking did was actually wrong? So it's semi-classical gravity, then now we have this sort of uncomfortable thing where it appears to be right and wrong at the same time. So again, the information paradox is an apparent breakdown of effective field theory of semi-classical gravity where it should be valid. And again, one possible conclusion has always been that we just don't take effective field theory seriously near the event horizon. But if we did that, we'd be throwing out the baby with the bathwater, because we can't get the quantum extremal surface formula without taking effective field theory somewhat seriously near the event horizon. If we just say that, here be monsters, this is full-on quantum gravity, then we've also lost the page curve calculation. So it seems to be that a route towards a resolution of the black hole information problem is understanding in what ways effective field theory is right and in what ways it's wrong in a black hole setting. So let's talk a little bit about ways in which it's right, ways in which it's wrong, and in particular, the process of accessibility of information. And what I mean by that, we're looking for a resolution. Let's talk a little bit about the microscopics of what's happening here on a quantum information theoretic level. So if you throw a diary into a black hole, then we expect that if the black hole is undergoing evaporation, sometime later, the information will be accessible in the radiation. What I mean by that, you throw a diary into the black hole, sometime later, you'll get this cloud of radiation, and if you have a quantum computer, you'll be able to execute some code that will yield for you the contents of the diary, and you'll be able to read the diary. And this was formalized in the Hayden-Preskill thought experiment. So here we assume that black hole dynamics are drawn from a unitary 2 design. And what we mean by that is just that the first 2 moments of this unitary are going to be drawn from the Haar random distribution. You take an old black hole, meaning a black hole that's past the page time, after the turnover. So the radiation has already started purifying. And we'll call its radiation E. That's the E system. The black hole system is the B system. We imagine we throw some qubit in a state I into it. This is the avatar of our diary. Then the information is recoverable from the radiation in a time that's logarithmic in the entropy of the black hole. And essentially, when we say recoverable from the radiation, what we mean is that there exists an operator V that can act just on the early radiation and the late radiation, E is the early radiation, meaning the radiation before you threw the diary in. L is the late radiation, meaning the radiation after the diary was thrown in. So there's an operator, V, that acts on the union of EL, on the radiation after the diary's been thrown in. And you act on the state of the black hole. B prime is the state of the black hole after L has radiated away. The union of the black hole, the early radiation, and the late radiation. And what you can get is essentially you can distill the state of the diary into factors of the Hilbert space of the radiation, where this state phi over here is essentially it's something that we understand. So it's always going to be the same, in some sense, the same thing. So this allows you to distill the information of the diary from the radiation into the same state that you can read it. Now, okay, this is how the information becomes accessible in the radiation, but there's a catch. The catch was discovered by Harlow and Hayden, where they showed that, sure, there exists such an operator. There exists a process that you can do. You can take the radiation and process it and distill the diary. But this decoding process of the radiation is exponentially complex in the entropy of the black hole. And they had an argument using some quantum statistical zero knowledge, but there was also a very elegant argument by Scott Aronson that followed, where he argued that if decoding the radiation were polynomially hard in the entropy of the black hole, then there would be no injective one-way functions, which is something that's widely expected to be false. So we expect that decoding the radiation is an incredibly difficult task, exponentially hard in the black hole entropy. Well, here is a proposal, which is very recent. It's from this past July with my collaborators, Chris Akers, Daniel Harlow, Jeff Paddington, and Shreya Vardhan, which is essentially the following. If you are simply computationally bounded and you don't have access to exponentially complex decoding protocols, you don't have the computational power, you don't have the access to computationally complex information, then you'd simply conclude that the information did not escape in the radiation. You have to have an incredibly powerful quantum computer in order to conclude that the information has escaped. And so we proposed to use complexity as a cutoff, similar to using energy as a cutoff in effective field theory. So we proposed that semi-classical gravity as an effective field theory accurately describes all the low curvature physics that can be measured by any observer whose computational power is bounded to be sub-exponential in the black hole entropy. Now, there are violations of effective field theory of semi-classical gravity at the event horizon, but only for exponentially complex observables. These violations are, in fact, critical for resolving the black hole information problem, but they cannot be detected by any sub-exponential observer. Now, there's a theorem called the small corrections theorem, which tells you essentially that small corrections to semi-classical gravity, so small corrections around the event horizon cannot add up to get you out of the black hole information paradox. But this gets around that because these corrections can be very large, but simply inaccessible to a sub-exponential observer. So this complexity as a cutoff gets around many of the issues of why semi-classical gravity appears to be valid, but isn't really. So this is a proposal. Does it work? Well, what do we mean by does it work? What would it need to do in order for us to conclude that it works? Well, what we want to do to resolve the information paradox, this is meant to a proposal towards a resolution. So what we want to do is we essentially want to resolve the following three facts. That there's a unitary S matrix, in other words, evolution is unitary. That there is a finite black hole entropy with state counting interpretation, that we have these black hole microstates that we can understand with some quantum gravity. And that there is a black hole interior, which is described to a good approximation in the regime where curvatures are low by gravitational effective field theory. Now, if we modify this last point, so it instead becomes there's a black hole interior, which is described to a good approximation by gravitational effective field theory for sub-exponentially complex measurements, then we found that there are models that have a decent description of black hole interiors, that of the black hole process, that can accommodate all of these three. So this is a slide sort of more for the experts in the audience. In a tensor network model of the black hole evolution process, tensor network describing the quantum gravity process, and also the map between effective field theory, semi-classical gravity, and quantum gravity. We can actually argue that we show that this works. So we model the map. So here we have some quantum circuit that we use to model the quantum gravity evolution of a black hole. Essentially, it involves applying a unitary operator at each stage to the black hole and having some radiation come out. And we have a map, V, that goes from the effective description from semi-classical gravity, which is essentially everything over here, to quantum gravity. And this map is given essentially by this tensor network model. Now, we find that this model, which I'm not going to tell you too many of the details, this is a little technical for this talk, but essentially this model can accommodate all of the requisite elements, 1 through 3 that I mentioned. And there are indeed significant violations of effective field theory at where the event horizon is in this caricature, this toy model, but they're completely undetectable to a semi-classical observer. And a very nice conclusion of this model is that if you wanted to compute the entropy that quantum gravity computes using effective field theory, then you would use the analog of quantum extremal surfaces in this model. So just 1 or 2 more words on this, and then I'll wrap up the talk. So this map V that goes between the semi-classical gravity picture and the quantum gravity picture annihilates a very large number of states that don't have any image in the quantum gravity Hilbert space. Now, this was actually a feature, not a bug. This is a non-isometric map, which you might be worried about if you've been talking about isometric codes. But this is a non-isometric map, and it actually is a feature because there's this problem that the Hawking radiation is too mixed after the black hole, once the black hole is finished evaporating. It's more mixed than the dimension of the Hilbert space that you started out with. And this is a phenomenon known as what we call null states, where we expect there are many states in semi-classical gravity that appear to be valid, but actually don't exist in quantum gravity because the quantum gravity Hilbert space is too small to accommodate them. And the fact that this map just annihilates those states by virtue of being non-isometric is a feature that resolves, a very important problem within the black hole information paradox. And again, what's fortunate and rather shocking to me is that we were able to do this without having any imprint on the experience of sub-exponential observers. So this is the non-isometric nature of this map is undetectable. The null state, the fact that there are null states is undetectable to a sub-exponential observer. A sub-exponential observer concludes semi-classical gravity is indeed valid. But there's this huge amount of hidden wealth of things here that are just, only accessible with exponential complexity. So let me go ahead and conclude. So the black hole information problem is a long-standing paradox in modern theoretical physics. It's an incredibly deep and fundamental problem about our understanding of the universe. And it's very exciting because in a little over 3 years, we've actually come to understand so much about it, especially when you compare it to what happened in the previous 40-something years, which is, far slower progress. And we've come to, to understand how we might use semi-classical gravity to work towards a resolution. And we found that quantum extremal surfaces are really an essential part of understanding how and when semi-classical gravity is valid. And we used that to give a proposal for potentially resolving the paradox that works in toy models. And of course, now we're working on going beyond toy models and incorporating different aspects of gravity that are not obvious in a tensor network model. So stay tuned, and thank you for your attention.
Thank you very much. Thank you. Okay, so thank you very much for the nice talk. And I think it's time for questions. So if you have any questions, then just please just unmute your mic and speak up.
So can I ask a question? So yeah, thank you very much for very beautiful talk. And my question is about your complexity cutoff. So
Yeah.
I think it's quite interesting idea. But on the other hand, we can find the quantum extremal surface relatively easily. So
Yes.
do you say, but it's quite difficult to see inside, I think this, black hole interior. But so do you think why we can find this quantum extremal surface so in something easily using effective field theory description?
Yeah, so let me go back to this over here. Yeah, so the quantum extremal surfaces are part of the effective description. We can find them, of course, using the language of the effective description without a problem. I think that the sort of the question that you're getting at is why is it that something that we can find easily computes this high complexity quantity? And that's an aspect of this map between the effective description and the quantum gravity description, which is very nice. So the map essentially incorporates in it it's a relation between effective field theory and quantum gravity, and it tells us that quantum extremal surfaces, at least within this toy model here, quantum extremal surfaces are the things that compute the von Neumann entropy. Now, I want to emphasize here that knowing that they are the things that compute the von Neumann entropy, that's the thing that's high complexity. Computing them is within the regime of effective field theory. But the thing that's complicated, the thing that's within the purview of quantum gravity in a sense, is knowing that this is the right calculation to do to get the von Neumann entropy. And in the language of ADS-CFT, that just boils down to the complexity of the duality itself, right? The ADS-CFT dictionary, I would say in some aspects of it are exponentially complex.
I see. So yeah. So the evaluation of entropy itself looks very easy compared with recovering the state.
Right, exactly.
Just wanted to, understand some that's
right. Yeah, the complexity here. Yeah, that's right. The complexity here comes from the dictionary itself, from knowing that what you're supposed to do is compute the QES. Yeah.
Thank you very much. One more question is, how do you think about the black hole singularity in this context?
The black hole singularity?
Yes.
Yeah, so the black hole singularity is I go back and forth on the black hole singularity because it's not clear to me how important it is to the story, which is important already at the level of the page time, where we're pretty far from the black hole singularity. There's also the fact that there exist solutions to the Einstein equation with fairly ordinary matter that are black holes that don't have a singularity. So these are called regular black holes. And I think that there's still an information paradox for those black holes. So I think there are aspects of the black hole information paradox that are maybe special to black holes with singularities, but I'm not convinced that the singularity is an essential part of the story. Of course, within this model over here, essentially what we do here in this going from here to here, we do post-selection. And there's this beautiful, the Horowitz-Moldesena proposal that implements post-selection at the singularity. And we thought for a while about whether there are similarities to our model. At the end of the day, I think the similarities are essentially just in the implementation of post-selection, because it's not important for us where the post-selection happens geometrically. So while there could be a role for the singularity here, in this context, it's not obvious to me that there has to be.
I see. So maybe then, if we somehow smear singularity, maybe a little bit, closer to your model.
Yeah. We can certainly. So so I can tell you what I think is missing from this model for it to be a genuine description, a complete resolution of the black hole information problem, which is, in my opinion, what it's missing is two things. The first is diffeomorphism invariance. We don't have that in a tensor network. And the second one is the question of typical states. So this is these are black holes that are formed from fast collapse. And so we don't deal with the problem of typical states, which is of course crucial for understanding firewalls. So I think it's missing those two, but to really model, at least even model fast collapse well, we need to find a way of incorporating diffeomorphism invariance here.
I see. Thank you very much for a very clear explanation.
Any other questions?
Sorry, I have a naive questions. So for unitary evolutions of quantum mechanics, the entropy will not increase. So suppose the universe is a pure state, does that mean that the second law just predict the entropy will not will just stay the same?
Yeah, it's a great question. So there are two different entropies to be discussed here. There is the fine-grained entropy, the von Neumann entropy, which is minus trace of rho log rho. And definitely that does not increase, that just stays constant. But then there's the thermodynamic entropy, which involves some kind of coarse graining. Maybe you're coarse graining over microstates. Maybe you're looking at something like a canonical ensemble. You're looking at all states with certain energies. And in that case, you will get a thermodynamic entropy, which will increase with time as your coarse graining gets progressively more violent in the sense of discarding more and more information. But the fine-grained entropy never increases for a pure state.
I see. Thank you.
Hi, thank you for your talk. So I want to ask two questions related to the last statement you make. So the first question is that when we talk about decoding the black hole interior for a semi-classical observer, and when we talk about like what is the time complexity it has, I think we need to specify a kind of computer this observer holds. So in this case, like what kind of computer does this like observer hold? Is that a quantum Turing machine or some other things?
It's an excellent question. So the proofs here, you could think of it as, I suppose you could think of it as a Turing machine, a quantum Turing machine. At the level of the proofs here, when we talk about the complexity, we really essentially mean we're talking about complexity classes. That's how the proofs work. And so, but for example, Scott's proof that this is high complexity, that the complexity is exponential unless there are no injective one-way functions. So that's an example of a proof where we essentially assume that it's within its complexity class. So I don't anticipate that this depends on the type of quantum computer you have. It's really an impossibility constraint. For any quantum computer, if your problem is in a given complexity class, then that's the complexity. You don't expect to be able to have by definition, you're not going to have a quantum computer that's more efficient than that complexity class. So this is really essentially for any quantum computer. I suppose when we visualize this to ourselves, we often think of a quantum Turing machine, but we don't need to restrict ourselves in any particular way.
I see. Thank you very much. And based on that, I have a second question. That is, we know that like even for kinds of machine, the time complexity may be exponential. Sometimes for much more like powerful machine, it can be polynomial complex. So in this case, if we want to make this question polynomial complex, what kind of machine do you expect what do you expect we need for such a task?
It's impossible. It's impossible. Yeah, I think there is no, the statement is essentially that there is no machine, no quantum computer for which this task is polynomially complex. If there were, there would be no injective one-way functions.
As like even if you have some non-deterministic Turing machine or something
that's much.
Right. I see. Thanks. Thank you so much.
Well, can I ask a question? Is it okay? Yes. I have two questions. So first one is what is your definition of effective field theory? I'm interested in where is the diversity of effective field theory encoded in this tensor network description?
So the tensor network description is it's a toy model. So when we say that this is typically when we say effective field theory, we mean that there is some energy cutoff. If we're talking about just quantum field theory, or in quantum gravity, we mean that there is both an energy and a space-time curvature cutoff. The two are related. So when we say effective field theory, what we mean here is that we're taking this tensor network, which describes the effective field description, seriously only when we're long enough after the black hole formation that we don't have to, that there aren't processes happening on, basically Planck times, and enough before the black hole evaporation process that we're not dealing with Planckian curvatures either. So this is a caricature that's meant to say, all right, so this is an intermediate time in the black hole, the smallest intermediate times in the black hole. In general, our definition of effective field theory, as we argued here, has to be modified to accommodate this complexity cutoff. That's essentially our argument. Does that address your question? I'm not 100% sure that I understood exactly what you were asking.
Yeah, okay, I understand. And my second question is regarding the very last part of your talk. So is a microstate counting reminiscent of counting Schmidt rank in the state in the Hilbert space of quantum gravity, or what does a microstate counting really do?
Essentially what we mean here is that we can think of the black hole entropy as essentially counting the states in the Hilbert space of quantum gravity that are consistent with the black hole exterior. So you could imagine that there are some states in quantum gravity that are not consistent with the given fixed black hole exterior. This is a bit of a toy example. I'm glossing over some important details, but the rough idea is if you say, okay, I'm going to take the black hole exterior, and I know that doesn't change, then what's the entropy of the black hole interior? Then you say, okay, well, it's the black hole interior can be anything that is consistent with what we observe with the black hole exterior. And so that's essentially the what we want is that for this entropy, this area of the horizon over 4G should be equal to an entropy that counts the number of states in quantum gravity that are consistent with a given fixed black hole exterior.
I see. So the exterior is described by effective field theory in that case?
Yes, up to exponential complexity.
Okay, it's now clear to me. Thank you.
Any other questions?
Hi, Netta. Thank you for the nice talk. And so I have two questions. And so first one is, so do you know what? So in Ryutaka Energy case, we have some homology condition. And so do you know what happens for quantum extremal surface case? Do we have some such a condition?
Yeah, we also have a homology constraint. It's very similar to Ryutaka Yanagi. It's marginally more complicated, something that we call Z2 homology, which is actually the way we should be thinking about Ryutaka Yanagi also, but it doesn't really come up in that case. But we certainly have the homology constraint. You can't just take a QES that's not homologous to the region. You have to be a little bit just a little bit more careful about what you mean by homology. So I mean I think you're referring to this sort of island proposal where you say, oh, the QES is sort of not is not homologous. It essentially is homologous if you bind into ER equals EPR. So that's here's one way to think about it, right? Let's take let me go to the early on, actually, Yeah, there we go. So let's take this QES here and we say, okay, it computes the entropy of the radiation, but it's not homologous to the radiation. So how should we think about that? So here's one way to think about it. We take this is certainly homologous to this boundary CFT. And then we say, all right, let's consider some what we call the canonical purification of the state of this dual CFT. And what that looks like is essentially a CPT conjugation of this Cauchy slice, which will give you another copy of the space-time and of this wedge over here, and generate a second CFT over here. Now, this QES is homologous to that second boundary by construction. And then you say, all right, well, that second bound, the state of that second boundary is a purification of my original CFT. And this radiation here is also a purification of that CFT. And since any two purifications are related by a unitary, then you know that if this QES computes the von Neumann entropy of one purification, it's going to compute the von Neumann entropy of the second purification. So this is one way of seeing how you get around the homology constraint that from this so-called island formula.
I see. Okay. Yeah. Thank you. And another question is about the last part, the toy model. And so, do you have any suggestion when we have some sub-exponential complex operation on that? So, for example, what happens for the bulk side when we apply such a complex operation? Do you have any suggestion from your model?
So you mean what happens, for example, if I imagine that I want to act on the radiation and cause something to happen in the black hole interior?
Yes.
Yeah, so I mean, it's going to be some extremely high complexity operation. Now, I don't have the slides on hand to show you what that looks like, although we did do that, but I'll try to explain it just using this picture. So let's suppose we can think of this in some sense as something like a precursor. So suppose we want to turn on some operator in the black hole interior, then and we want to do it by acting on the radiation. We can say, okay, we're going to act on the radiation, but really we can evolve this backwards in time until that, imagine we turn on some perturbation here, this sort of propagates into here, and it evolves forwards in time in the radiation. So we can think of that as, causing us to have turned on some operator in the radiation. Now, you can say, oh, well, that doesn't look, that complex. And the problem is it's very different turning it on over here versus turning it on over here. If we turn it on over here, what we've done is we've essentially disrupted the structure of the modes at the event horizon. And the Transplanckian effect is going to magnify that and create a singularity down here. You can actually work through the math in this in JT plus a CFT and show that there's no way to evolve that perturbation backwards to a point here where it would have been simple to turn it on. So you can see that this is a manifestation of the complexity of acting on the black hole interior, where essentially if you act something over here, if you try to turn something on, it's going to disrupt the modes here. It's going to cause a singularity to appear, and then you're not going to be able to evolve this backwards using simple Einstein equations to put backwards in time evolution. So that's sort of a way of seeing that you can't use the semi-classical equations to do the simple evolution to recover this thing that you did on the radiation just by virtue of how you've disrupted the system by doing it. It's there's a nice set of pictures in the paper if you want to look, where we discuss the Python's launch story and how it applies here, where we showed essentially that doing this kind of thing is going to cause a singularity to appear and prevent you from doing something simple.
So where is the singularity if we evolve backward around this point you wrote CF? Sorry. Where is the singularity when we?
Yeah. Right. I mean, if you look at the holographic complexity, the Python's launch proposals, I had a paper with Jeff and Arvin where we essentially argued that if you take a black hole, a single-sided black hole, or it can be a two-sided black hole too, just take a black hole and you try to do anything to the radiation and anything to the interior using the radiation, you're basically going to incur a huge amount of back reaction and destroy part of the space-time. So you lose, so basically semi-classical gravity, you lose control over it, it becomes, there's singularities and you clearly see that there's some quantum gravity mess going on. So yeah, so you can computationally see this. And yeah, I don't have the slides, unfortunately, but if you look up the second paper I wrote with Jeff and Arvin, or we also review it in this paper with Daniel, Shreya, and Jeff and Chris.
Okay. Yeah, anyway, so I think so if we try to evolve back then, so we have some another horizon.
Right, yeah, you hit up against, you can't, yeah, you find that you can't, yeah. You have to evolve through a singularity and only quantum gravity knows how to do that.
Okay, yeah, thank you.
Okay, any other questions? Okay, I think it's good time to start my questions. And actually, we're gonna have online midnight coffee time at a spatial chat. So if you have further questions and also if you have time, please join us. You can find the link to the spatial chat at on this Zoom. So before closing this colloquium, let's thank Netta again. Thank you very much.
Great.